right, thank you, fellas. Absolutely honored. Again, in terms of like passing people throughout the community, I think, yeah, we've done several laps. You're on my wall. So
good.
There's more room too. Just saying. If I can ever get one of your auctions. But yes, no, I'm a huge supporter of the arts, and so building this relationship with Shelley has just been an honor for me. I've always trying to figure out how we can combine the world of business and of science with the arts, because there are no better communicators of the world than artists. And I think a lot of scientists could actually learn a little bit from the art world. And so that's one of the reasons I was so excited to go ahead and move forward with this. So if you were able to join us for our last talk, I did give a brief introduction to light. And in talking with Shelley, we realized that gravity would actually be the next natural iteration of this series. And so if you were not able to join us, and this is your first physics class ever, welcome. Don't be scared. One of the things that's really important to me is that we do make physics and the world of science accessible, because it's pretty darn cool. Otherwise I wouldn't have spent so much time studying it in basements without windows. So without further ado, I'll go ahead and get started. So what is gravity? We all feel it every single day. It has a few different definitions, and so pardon the size of the font. I will read these out, and it's more just for impact than actual knowledge. You don't have to memorize this. There's no test at the end. In the English language, gravity is dignity or sobriety of bearing, importance or significance. And so I think that, as we walk around day to day, we think of, the gravity of a situation. Now, in science, gravity has a very different meaning, but it is no less serious. It's the gravitational attraction of the mass of the Earth, the Moon, or a planet for bodies at or near its surface. Notice that the definition is a lot longer when we're talking about science. Once again, science is not as good at communicating itself as artists are. A fundamental physical force that is blah, 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 blah. We'll get into that. Also, when you're studying gravity, you'll see a lot of drawings like this. This is about as artistic as most scientists get. It's a lot of Greek symbols, a lot of Latin, a lot of capitals, and a lot of letters with little subscripts because we run out of letters to describe things. But I want to give a brief history of gravity while you stare and get dizzy by this. The ancients didn't really think of it as a force in the same way that we do today. Most people in general don't give it a lot of thought, but of course there are scientists, and we do tend to think about things that nobody else does, often in basements without windows. They thought of it as like a natural predisposition of things to just fall towards the center of the Earth. They didn't really have a concept of force, at least not until Newton's time. And so the famous image we all have of Isaac Newton with the apple falling from the tree and hitting him on the head as if he had some kind of eureka moment. In fact, he was actually hiding out from the plague and had more than enough time to do things like, if you were at our last talk, I mentioned him poking himself in the eye to try to figure out where color comes from. But he also did a lot of work in mathematics to try to figure out what gravity was, this idea that it's a force. And it's actually one of 4 fundamental forces. So we have gravity. We have electromagnetism, which gives us light and all sorts of good things. We also have what's called the weak and the strong nuclear forces, which are pretty poorly named, because actually the weakest of the 4 forces is gravity. And here's how it works. It is a force, which means that it's a push or a pull. But in gravity's case, it's actually just a pull. Gravity is the only one that is only an attractive force, and it pulls us towards a mass. But what that mass is doesn't actually matter. Every single mass has pull. So each of you sitting in this audience right now are actually pulling each other towards one another. It's just that the Earth is so much bigger that it's pulling you a little bit more. I love that. So what does gravity do? It brings us together in really specific ways. It is responsible for causing all of the stars and planets to stay in orbit with one another. Because again, they all have some mass, and that mass is all pulling towards each other. But because there's more than just two objects, it becomes this really incredible dance throughout the entire universe. So how does gravity impact how we perceive the world around us? Fun examples, of course, are like astronauts, Marcia Ivins. You will see their hair floating as they're up on the International Space Station. Astronauts, I think, get to have the most fun with gravity, or the lack thereof. And the picture on the right, and I'll talk a little bit about this in a few slides, is actually the first real image of a supermassive black hole. This is a real picture. This is not an artist renditioning. This is actual scientific data. And black holes aren't something we even knew about until about 100 years ago. The most common way we think of gravity is in terms of weight. But it is nice to think that on the moon, you would actually weigh 16% of what you weigh on Earth. So if you are partaking in the cookies, just think that you're going to just care about how much you weigh on the moon. And this is kind of a fun comparison as well. If you weigh 100 pounds on Earth, physicists also like really round numbers. We like ones, we like tens, we like 100. We really like zeros. Zeros are the best, because then you can cancel all sorts of that math out. But if you weigh 100 pounds on Earth, you'd weigh 17 pounds on the moon, give or take. 38 pounds on Mercury, still doing pretty good, although it is not super habitable. 91 pounds on Venus, and a whopping 253 on Jupiter. Wow. So just in terms of how those masses and the size of those planets dictate how we experience gravity. And that's when we're really close. Now, something that a lot of people don't know is that gravity is not constant on Earth. So while there is a gravitational pull towards the center-ish, that pull varies as we go across the surface of the Earth. So in terms of anomalies, it actually is a pretty wide range from blue to red. Don't worry about the units, we're not getting into that. But you can see that there are areas of the Earth that have slightly less or slightly more than the scientific gravitational pull that we say is 9.807 meters per second squared. Again, don't worry about units, there is no test. Most of what we understood about gravity is based on our own experience, and that's understandable for scientists. We try to figure out the world around us, and the world around us is pretty close to the surface of the Earth. But of course, there are always those scientists that are looking further out, and they're looking at trying to figure out how gravity impacts the universe. And up until we understood that gravity was a force, it wasn't even related to the motion of the stars and planets. We thought those were totally different things, but it's all one thing, gravity. And so we got to go back to this guy, because he really likes to shake things up in the world of physics. So Albert Einstein, one of his more famous contributions is the general theory of relativity. This actually comes in two parts. So in terms of special relativity, there's this discussion about how nothing can go faster than the speed of light. So we talked a little bit during the last series. It also talked about things that go really close to the speed of light and how that impacts our perception of time. Things like astronauts actually being younger when they come back to Earth than their twin brothers, who are also astronauts. I'm looking at Mark Kelly right now. And that is a proven thing, that now that we actually can put astronauts into orbit and they happen to have identical twins, we can actually look for genetic markers that show that they are slightly different ages now, but very slight. There's not going to be a different birthday anytime soon. But Einstein's contribution to general relativity really shook things up. Now, he didn't get his Nobel Prize for this. He actually got that for doing some investigations around electrons. Maybe that'll be another talk. When forced to summarize the general theory of relativity in one sentence, and there are thousands of pages of writings on this theory, so one sentence: time and space and gravitation have no separate existence from matter. So what does that mean? Well, for one thing, it was theorized that there were black holes. These singular points in space with basically infinite or very, very, very high masses that are so super concentrated into that one spot that the gravity of it becomes absolutely impossible to escape from, even for light. How the heck are we supposed to see one of those? Because if it sucks everything in, even light, that takes away one of our key ways of finding out about the world around us, which is looking at light and radiation. Luckily, because of the way light and mass orbits around these black holes, they actually have a bunch of really cool aspects that we can see. They have what's called the accretion disk. So this is literally mass and radiation that's being spit out from these black holes because of how fast everything is moving around them. They have what's called an event horizon. That's kind of the point of no return. There's some good horror movies around that. And then of course you have the singularity at the center. And so this is why we were able to actually take a photo. And so this is an even more recent photo of a supermassive black hole. And so yes, they exist. General relativity predicted it, and now we can actually see them. And it's anticipated that there's billions of these, even just in our Milky Way galaxy. It's even theorized that maybe there are teeny, teeny, tiny microscopic ones that are flying through the universe at any given moment. Don't worry, they're not going to suck you in. They're not vacuums. The big thing with general relativity is this idea that the universe isn't flat. Most of physics depends on this idea that you go this way, and you can go this way, and you can go that way. And you can do some spinny stuff. But that it's uniform throughout this coordinate system that we establish. It makes all the math work, and especially when we get to little stuff. Well, general relativity ruined that. It says that gravity of objects actually bends space in the same way that if you drop a bowling ball in a trampoline, the trampoline bends. And so that the gravitational pull isn't so much a force, but a consequence of the bending of space-time. So you have these marbles, these moons, these planets, these galaxies that are orbiting around things like black holes because they're literally falling into this bent and curved space-time. And it's not just planets and things that we usually think about with mass that do this. The curvature of space-time bends light, which actually gives us a really good tool to see even farther away. Supermassive objects can become lenses, just like a telescope. What you see here is called an Einstein ring, named after that guy. That is actually a galaxy behind this star. The light is bending around it because of its gravity and because of its significant mass, and it's doing so in just the right way so that we look at it and we can actually see it, but we see it in pieces. And there are traces of this in all sorts of images of deep space. Let's see if this is actually going to play. Nope. I'm going to go back. What you see here is two black holes. And this is an artist rendition. This is an actual photo. These black holes, because of their incredible mass and their incredible gravity, are actually orbiting one another. And as they do that, that's not an easy thing to do. So they're losing energy. They're colliding in on one another. And while they do that, they're actually sending ripples out into space. And these ripples travel at the speed of light, bending space as they go. This was something else that was theorized, and actually when I was an undergraduate, hadn't been proven yet. So in the early 2000s, there was an experiment being built to try to measure this, because these things, this actual collision happened 1.5 billion years ago. But we found it. And this is how. Something called the Light Interferometry Gravitational Observatory. These arms, those tubes on either side, are 2 kilometers long. There's one of these in Washington and one in Louisiana. And you have to have both. Because as these ripples go through space, we can actually detect them, but they're so subtle that we need to see the differences really far apart. And so we took thousands of miles, but scientists working at both of these were able to put that data together and confirm in 2016 we saw it. They were able to see that ripple in space and confirm yet another postulate of Einstein's general relativity, that gravitational waves exist and we can measure them. Something that's being worked on now is quantum gravity. So we know that we can see these waves. We know that gravity pulls things together. What we don't know is what happens when things get really, really small. And this is where the theory of relativity actually butts up against the standard model. And so this is what describes things like protons and neutrons and quarks and these subatomic particles that are flying really, really fast at places like CERN. When we get to things that are really, really small, it breaks down. And it breaks down because in the standard model, we need everything to be flat. But general relativity makes it all curved. And so now we're talking about things that are moving on curves and around what's called geodesics. And that doesn't work anymore. And so scientists are now fighting with each other over how to describe this and to actually compensate for this. So some think it's these little strings. And so they have string theory, and it's these little tiny strings that are in such high dimensions. We're not talking 1, 2, or 3 dimensions like we experience. We're not talking about 4, like how we experience time. We're talking about 10 dimensions, 11 dimensions that don't even make sense. And that maybe that's why we can't figure out a way to have an experiment that observes them yet, because we don't know how to measure things beyond 4 dimensions. There's another idea that's called quantum loop gravity, which basically tries to turn all of space into geometry. And so it's like you have these little tiny points and you create these curves around them. And along this topology, everything works. But they're fighting, so we don't know. Maybe we'll figure it out in 100 years. And I think Feynman put it really well. So another famous physicist who was one of the great teachers of physics. There is always an edge of mystery. Always a place where we have some fiddling to do. But the most impressive fact is that gravity is simple. It is simple, and therefore it is beautiful. Finally comes the universality of the gravitational law and the fact that it extends over such enormous distances. And so that is what I want to leave you with. Thank you.